Hello, Devoxx Ukraine. It is lovely to be with you guys again. And welcome to this session on thriving in the cloud, going beyond the 12 factors. My name is Jansen, and I'm a developer advocate at IBM based in the UK. If I don't get around to answering any of your questions, or you think of something later on that you'd like to ask me, I am available on Twitter, so feel free to go and follow me or send me a tweet at GraceJansen27. So without further ado, we'll jump straight into this session and find out how we can go beyond the 12 factors to really enable our applications not just to survive in the cloud, but to really thrive in the cloud. So let's take a look at first at our evolution to the cloud and why we now need to take a look at how our applications can be evolved to really take advantage of this infrastructure evolution. So our underlying infrastructure has been evolving over time to be able to offer us the fantastic array of sort of resources that we now have at our disposal within the cloud. So whereas previously we used to be using a single core, we can now take advantage of multi-threading and multiple cores. We can now make use of this naturally distributed environment within cloud infrastructure and enable our applications to make use of things like virtualization and containerization. So we now have all of these benefits from sort of new, evolved, modern and improved infrastructure. And this meant that we needed to evolve our applications to be able to take best advantage of all of these benefits. So we evolved our application from sort of these more monolithic applications that were perhaps larger, bulkier, usually all in one. And we evolved that into sort of more broken down applications. So whether that's macroservices or microservices, we now have sort of individual aspects of our application or components that are linked together across this distributed infrastructure. And this was a fantastic step forward because it allowed our applications to be easier to debug. We could take down single aspects of our application and replace it without needing to tear down our entire application and get it back up and running again. It also enabled us to be able to replicate just one single component rather than have to replicate the entire application, to be able to enable us to deal with load better as well. But this application evolution hasn't finished. There are still steps that we can take to enable our applications to make better use of this underlying infrastructure and enable us to really thrive in the cloud. So why do we even care about enabling our applications for the cloud? Well, the cloud is exciting. If you've seen Toy Story, you might know this reference, like, ooh, the cloud, instead of the claw. We got excited about cloud because it offers us a whole bunch of sort of advantages and benefits that we can make use of within our application. So what does the cloud offer? Well, these are some of the advantages that you can gain from utilizing cloud infrastructure. Cost, for example. The cloud infrastructure, essentially, especially if you're using an external cloud provider, you're essentially offloading that to a central provider, and they're able to do that at scale because they're getting these requests from multiple different organizations and applications. So they're able to do this at scale, which enables them to have economies of scale. So they should be able to run this cheaper than if you were running it individually, and so they should be able to pass some of those cost benefits on to you. Also, scalability. So being able to rapidly scale up and down the resources that you're utilizing for your application because the underlying infrastructure is already there ready for you. So you're able to scale it depending on the load to your system or perhaps needs at the time. Speed, you're able to do that at extremely fast speeds, being able to spin up something almost immediately if, for example, you don't have, say, cost limitations on those resource allocations. So because that infrastructure is there and ready to use, you're able to implement that use of that infrastructure and those resources fairly quickly. And you're able to make use of sort of very comprehensive infrastructure, which enables you to have a much faster application. Resiliency. So if one data center were to go down, being able to utilize a different data center or a different rack, for example. So having that resiliency because you don't just have a single rack in a single location, you're utilizing this shared cloud platform. So your application could be moved if there was a potential problem, for example, enabling you to have greater resiliency because your application doesn't completely go down if that one rack or that one server and that one data center goes down. So being able to move it around enables that increased resiliency. And flexibility. So if you need it to be in a particular location, for example, or having the flexibility to increase or decrease your resources, all of that is enabled within the cloud as well. Fashion. You might not think of the cloud or maybe IT as being a fashion industry, but it is when you think about it. We see fashions and trends and we get excited by them, like microservices or cloud or several other types of innovation that really enables us to get excited because it offers additional benefits and it looks cool. So actually, we are a fashion industry and we do often follow trends, etc. And the cloud enables us to really utilize that underlying innovation to be able to offer that up to our clients, offering additional benefits, whether that's faster application startup, greater ability to deal with increased fluctuations in load. All of this enables us, the cloud infrastructure enables us to utilize those fashionable trends and that underlying innovation to offer those benefits up to our end clients. So all of this is why we're excited about cloud and why we really need to be making best use of it for our applications. So what does it really mean to be cloud native? How do we build applications that are really built for the cloud? So I went to the CNCF for this. Arguably, by the name, they are experts in all things cloud native. And they define cloud native as technologies that empower organizations to build and run scalable applications in modern dynamic environments, whether that's public, private, or hybrid clouds. So really, it's about utilizing the underlying technologies, that evolution of infrastructure, to be able to run applications that are able to deal with the modern dynamic environments we're dealing with within our modern technology. And so actually, these technologies can differ depending on what your application needs. So it might be that you're utilizing containers or service meshes, microservices, or maybe declarative APIs to exemplify this approach. But the fact is, these techniques are all about enabling loosely coupled systems that are resilient, manageable, observable, and combining it with things like automation to allow us as engineers to enable high impact changes frequently and predictably with really minimal toil. So I then took a look at sort of a variety of different definitions from organizations, took out the technology specific or language specific aspects, and took a look at, okay, from all of these different definitions, what are the behaviors that I need to be implementing in my application to make it cloud native? And these were the different behaviors that came out of this overall sort of crunching of all of these different definitions of cloud native. So as I mentioned, a lot of these factors I already mentioned before. So observability, having this loosely coupled aspect to the components, especially in this distributed environment, enabling scalability, having resiliency and speed, being able to rapidly allocate resources, for example. So these are some of the most important factors when it comes to being able to really exemplify the cloud native approach and build applications that are able to thrive. So how do we actually go about, now that we know that we want to be cloud native because the cloud offers all of these benefits, it's really exciting and enables us to create applications utilizing a lot of innovation. We now know sort of what it means to be cloud native, so the behaviors that we need to be exemplifying within our application to enable our applications to thrive on the cloud. But how do we actually enable these behaviors when it comes to actually utilizing technologies to be able to build applications that are ready for the cloud? And actually, one methodology that I really enjoy and really like is the 12-factor app methodology for this. So this was a methodology that was defined by the developers over at Heroku for really building cloud-native applications. If you want to find out more about it, there is a website that you can check out. It's the 12factor.net website, and it goes into each of the factors in a lot more detail, but we'll be covering some of them today. Just if you wanted to go off and have a look yourself, you can. So it's essentially all about enabling our applications to be written in any language. So it's really a language agnostic methodology, and they can use any combination of backing services and technologies. These 12 factors are all just mainly about sort of behavioral changes that can be generically applied to any application. So the original 12 factors were codebase, which is essentially all about having one codebase that can be tracked in revision control, but you can have many deploys. Dependencies, so explicitly declaring and isolating dependencies. Configuration, backing services, build, release, run, processes, port binding, concurrency, disposability, dev prod parity, logs, and admin processes. Now, we'll go into each of these in a bit more detail through the 15 factors. The reason that this was basically the 12-factor application methodology is a fantastic introduction to the discipline of building and deploying applications in the cloud and really preparing teams for the rigor that's necessary to be able to build a production pipeline around sort of elastically scaling applications. But technology has advanced since the 12-factor methodology's original creation, and in some situations it is necessary to sort of elaborate upon these factors, as well as add new guidelines designed to meet sort of modern standards for application development. And so the original 12 factors was iterated upon to create the 15-factor app methodology. This was created by an author called Kevin Hoffman from Dynatrace, and essentially it's loosely based around the original 12 factors. You'll see some commonalities, but there are additional revisions to each of them, and there's additionally 3 new factors, which is API first, telemetry, and authentication and authorization. So we'll take a look at each of these and see how we can apply this, utilizing there's lots of open source options, but if you wanted to, proprietary, and taking a look at how we can enable these factors to then enable the behaviors for cloud native to make our applications ready to thrive in the cloud. If you want to take a look at the sort of origins of this 15-factor app methodology, the link to the book is there at the bottom of this slide. So let's take a look at how we can really thrive in the cloud by using this revised 15 factors. So the first factor is one codebase, one application. Now you'll notice on each of these slides that for each of these factors, I put just a little strip at the bottom. If it's a green strip, that refers to one of the original 12 factors. So in this case, it's the first factor from the 12-factor app methodology, which is codebase. So you can see where these sort of these different methodologies have similarities and sort of where this evolution has come from in the 15-factor app methodology. If, however, it's an orange strip at the bottom, that means it's one of the new factors. There's only 3 of them that have been added into the 15-factor app methodology. So one codebase, one application. What does it mean and why is it important? So this is all about having that, like ensuring that each codebase is stored in a version control and that there's a one-to-one relationship between an application and its codebase, but a one-to-many relationship between a codebase and its deploys, as you can see here, depending on where you're deploying to, whether that's production, staging, QA, dev, etc. Why is this factor important? Well, this is all about enabling collaboration between development and teams, enabling proper versioning, and enabling faster time to market. So how can we achieve this? Well, through Git repositories. So whether you're using GitHub, you might be using GitHub Enterprise or perhaps GitLab, or there are alternatives. So maybe you're using Bitbucket or Launchpad, or maybe you're using a cloud alternative like Google Cloud Source Repositories or AWS Code Commit. So by utilizing these Git repositories, we can enable this factor, having a one-to-one relationship between application and codebase, and a one-to-many relationship between codebase and all of our deploys. The second factor in the 15-factor app methodology is a new one. So this is about API first. Now, it's worth noting that some of these factors don't necessarily map to specific physical requirements that might be imposed by the cloud, but they're more about habits of people and organizations when it comes to building cloud-native applications. So what is this factor all about? Well, it's about giving teams the ability to work against each other's public contracts without having to interfere with the internal development processes. So API first is essentially, it means that you're building an API to be consumed by client applications and services. So really thinking about that API first, hence the name. Why is this important? Well, it helps us to avoid integration failures and to really formally recognize your API as a first-class artifact in that development process. And it enables greater collaboration with stakeholders, for example, really designing what they need from each API or service, creating greater documentation and the ability to be able to mock up these APIs first. By being able to mock them up first and really concentrating on what your stakeholders need, it really enables you to test and vet the direction in which you're taking your application and your plans before you actually invest too much time in supporting a given API. So it really enables you to test it first and make sure that your application is going in the direction that your stakeholders need it to and want it to. And it enables you greater flexibility because you can change it. If it's not what they wanted, if it's not what they needed, if your API doesn't quite meet the needs of those stakeholders, then you can change it without having wasted too much investment. So how can we go about achieving this? Well, it's all about being a participant in this ecosystem. So the first thing we can do is sharing public contracts. So we can utilize things like OpenAPI or the API Blueprint, both of which are open source specifications. We can also make use of tools that implement these open source specifications, like, for example, MicroProfile OpenAPI, or you might want to make use of proprietary products like Apiary or IBM's API Connect tools. There's also the OpenAPI initiative, it's OAI. This is focused on really creating, evolving, and promoting a vendor-neutral description format. So the OpenAPI specification was originally based on Swagger specification, donated by SmartBear Software. So essentially, we can utilize these open source tools and technologies to enable us to utilize a shared description language to be able to create these public contracts so that we can all work together to create APIs that work for our stakeholders and that can be utilized easily without having to interfere internally with the source code. That's what this is all about. Number 3, dependency management. So as you can see, this links to the second factor within the original 12-factor application. So this is all about essentially explicitly declaring and isolating our application dependencies. So we might make use of application declaration manifests, or perhaps use a dependency isolation tool during our application execution. So in classic enterprise environments, we're sort of used to this concept of perhaps having a mummy server, and that is a server that essentially provides everything that our applications need and takes care of every desire, from satisfying the application's dependency to providing a server in which to host the app. It does everything for them, hence the name mummy server. The cloud, however, is a maturation of this classic enterprise model, and so our applications, as a result, need to grow up. They need to take advantage of that cloud infrastructure. So our applications can't now assume that a server or application container will have everything they need. Instead, our apps need to bring their dependencies with them. When we're migrating to the cloud, we need to mature our development practices. It means weaning our organizations off this need for mummy servers. So this is where this factor really comes in, by explicitly declaring and isolating the dependencies that we might use. And why is this important? Well, it helps to provide consistency between our development, production, testing, etc., all of our different deployment environments. It helps to simplify setup for developers that might be new to the application, and it also enables greater portability between different cloud platforms, enabling greater flexibility for you guys as organizations, and it really supports greater developer productivity. So how can we enable this? Well, we can explicitly declare and isolate our dependencies utilizing, for example, third-party libraries inside your microservice. So instead of packaging third-party libraries inside our microservice, we can specify them in things like Maven and Gradle. So if you're using Maven, you'll be using a pom.xml. If you're using Gradle, you'll be using a settings.gradle file, enabling you to sort of freely move up to newer versions if you need to, roll back to older versions if you need to. So utilizing sort of Maven and Gradle enables us to isolate and externalize and really make sure that we have all of our dependencies in one place. What about number 4? Number 4 is design, build, release, run. Now, this is just an iteration on the original 5th factor, build, release, run. So you can see the difference here is really that addition of the design step. So again, you can see how from the original 12 factors, we've progressed when it comes to understanding what's needed to be able to build a cloud-native application, and thus the need for this iteration to include design. A single code base, really the design step is all about having a single code base that is taken through this sort of build process to produce a compiled artifact. So the design stage here is about designing small features that get released. We'll have sort of a high-level design that can be used to sort of inform everything we do, but we have to also know and understand that design can change. It needs to change depending on sort of feedback we get from end clients, different needs that we might experience as we go along this build process. And so we need small amounts of design should be part of every iteration that we do, rather than just entirely being done up front. So hence why it's been added into this cycle. It's during the design phase that sort of arrangements are made to declare dependencies, as well as the means by which those dependencies are sort of vended, bundled within the application. Then you have the build, the release, and the run stages, and they're pretty much standard. You're probably used to them all by now. But essentially, the build stage is where a code repository is converted into a versioned binary artifact. So it's during this stage that the dependencies are declared. During the design phase, they're fetched and bundled into the build artifact. And in the Java world, a build stage, for example, might result in a war or a jar file. The release stage. So in a cloud-native world, the release is typically done by pushing to your cloud environment. So the output of the build stage is combined with environment and app-specific configuration information to be able to produce another immutable artifact, in this case, a release, hence the name. So releases need to be unique, and every release should be ideally tagged with some kind of unique ID, like a timestamp or an auto-incrementing number, which you're probably used to by now if you've been utilizing, or other dependencies, for example, which probably use a similar sort of naming or tagging sort of factor. So then you have the run stage. So the run stage is typically done, again, by the cloud provider. You don't need to worry about it too much within your application itself. The details do vary among providers, but the general pattern is that your application is placed within some kind of container, whether that's Docker, Garden, or Warden, or something else, and then a process is then started to launch your application. So this factor is really about strictly separating out the various different stages of this cycle to help to prevent changes to code or configuration at runtime, to help lower the number of unexpected failures, to enable more effective release management, enabling maximum delivery speed, while also keeping a high confidence level through this automated testing and deployment. So how can we enable this? Well, there is a more methodology or practices thing for people in an organization. Again, this is similar to the other one I was talking about. It doesn't have to be specific to a technology. This is more about the practice of how you're actually going about building that application and going through this delivery pipeline. But you might consider adopting things like a CI/CD pipeline. So, for example, Tekton might be really handy with that. So what about number 5? Number 5 is configuration, credentials, and code. So this links to the third factor in the original 12-factor app methodology, which is all about sort of the original factor stated that you should only store configuration in the environment. This updated factor really aims to be more explicit with that. So essentially, it's about ensuring sort of strict separation between code and configuration, and storing that configuration in external variables. So why is this important? Well, it's about modifying application behavior without making code changes, and simplifying your deployment to multiple environments, reducing your risk of leaking credentials and passwords, which is a major security potential threat, and enabling more effective release management. Really, it's all about, credentials are extremely sensitive information, and they should have absolutely no business being in your code base, especially when so many of our applications are utilizing things like open source. They might be easily accessible through repositories, etc. So it should really be obvious why we don't want to include credentials, for example, in our code base. Really, the golden rule of microservices is that you should be able to write once and configure everywhere. So by externalizing not just the credentials for security, but also the configuration, we should be able to essentially be able to change that configuration if we want to deploy somewhere else, but the core code of our application should be able to remain the same. So really, it's best practice for us to be externalizing both configuration and credentials from our code. So how do we do this? Well, it's all about extracting all of our application configuration and enabling that through external environment variables. We can utilize things like microprofile configuration to be able to enable us to place those configuration variables within properties files that then can be really easily updated because it's all in one place. You know exactly where it is. You only have to update one value and then it will automatically propagate through your code without the need to, if you're updating it, you don't need to then recompile your microservices. We can also make use of things like microprofile or CDI injection to then directly inject a set of properties. If you've not come across microprofile before, definitely an open source project worth checking out. It's really community driven and it's all about enabling sort of applications that make use of Java or Jakarta EE to enable them to build applications designed for the cloud and microservices. So it offers additional APIs and behavioral components that could be and are helpful and important when designing distributed microservice-based systems if you're basing it on Java or Jakarta EE. So definitely worth checking out if you've not already. If you are interested in having a go at any of it, I have put some helpful links on some of these slides to interactive guides that you can make use of that show you how you can implement things like microprofile and various APIs. So check that out if you're interested. Number 6, logs. So what is this one all about? This is about treating logs as event streams. So really you should be logging to stdout or stdr only. So a truly cloud native application should never concern itself with routing or storage of its output streams. It should be just be treated as an event stream. This links into the original 12 factor number 11 logs, so title's the same. Why is this one important? Well, it makes logging a platform concern and not a developer concern. And it helps you to improve flexibility for introspecting behavior over time, enabling sort of real-time metrics to be collected and analyzed for your application. So how do we enable this? Well, as I mentioned, you should be logging to stdout or stdr, so log to stdout or stdr only. That's the first step. Secondly, you should be treating your logs as event streams. You might consider, for example, aggregation, processing, and storage of logs as a non-functional requirement that can be satisfied not by your application, as I mentioned, but by your cloud provider or some other toolkit or tool suite that might be running in cooperation with your platform. So there are various different tools out there you can use, like the Elk Stack, which is made up of Elasticsearch, Logstash, and Kibana. You might be using FluentD, there's Splunk, Sumo Logic. There's any number of tools that you can utilize that enable you to capture and analyze your log emissions to enable you to, as I said, make it a platform concern, not a developer concern or an application concern, and enable you to be doing best practice of logging to stdout and stdr only. Number 7, disposability. So this links into the original factor, disposability, same name. So really, this is all about maximizing robustness via fast startup and graceful shutdown. So really, the reason I've got this diagram up here, because this factor is all about being able to dispose of components in our application without really thinking twice about it. So an application can't scale, deploy, or release or recover rapidly if it can't start rapidly and shut down gracefully. So really, we need to be building applications that are not only aware of this, but embrace it to take full advantage of the platform. So really, our microservices should be fault tolerant and able to function under any situation, and they should be able to be disposed of and brought back up again without any issues. So the reason I've got this diagram here is really to demonstrate that we should be treating our app instances as cattle and not pets. Cattle tend to have numbers, they tend to be replaceable. If it gets ill, we tend to just sort of replace it with another cow or another cattle. They're very disposable, and that's the type of system we need in cloud native applications. We can't be having pets. Pets get given a special name, they have a close emotional attachment to the owner, they tend to, if they get sick, they tend to be nursed back to health, they're not just replaced. This isn't great for cloud native applications. We need to be able to have, as I said, fast startup and to be able to shut them down gracefully if we need to. So really, we need disposability. We need to be treating them more like cattle than pets. And this enables us to really be resilient to unexpected and sudden shutdowns. So why is this factor important? Well, it enables really fast, elastic scaling. It allows us to rapidly deploy new code or config changes and then it enables robustness in production, in deployments and auto scaling. How do we go about enabling this? Well, we need to minimize work on startup, so please don't be depending on things like shutdown hooks, and we need to be maximizing robustness with fast startup and automatic scaling. So things like microprofile fault tolerance can really help us out with this. Many applications are written that they basically perform a number of long-running activities during startup, like fetching data to populate a cache or preparing other runtime dependencies. But really, to truly embrace cloud native, this kind of activity needs to be dealt with separately. So you could externalize the cache, for example, into a backing service so that your application can go up and down rapidly without needing to perform these front-loaded operations. So microprofile fault tolerance can help out with this. As I mentioned, we need to be enabling that fault-tolerant behavior, whether that's to spin up another microservice or another instance, or whether it's to shut down and restart. That's dependent on what you enable within that fault-tolerant behavior. There's a guide here if you'd like to try checking that out. Number 8 is backing services. So when I say backing services, what I mean is essentially any service on which your application relies for its functionality. So it's a really broad definition, and its wide scope is intentional. Some of the most sort of common types of backing services can include data stores, messaging systems, caching systems, and really any number of other types of service, including services that perform line of business functionality or security. So this factor here is really all about treating these various different backing services as bounded or attached resources. So we should be making no distinction between local and third-party services. They should all be treated as bounded or attached resources, and we can attach them via the use of URLs that can be stored in our application's config. Really, when I say a bound resource, if you're not familiar with that, I really just mean a means of connecting your application to a backing service. So, for example, a resource binding for a database might include something like a username, a password, and a URL that allows our application to consume that resource. So importantly, there should never be a line of code in your application that tightly couples the application to a specific backing service. So why is this factor important? It helps us to provide really loose coupling between service and deployment. Remember, that was one of the main behaviors of cloud native applications, that loose coupling. It means that no code changes are required to be able to update our backing services if we need to. It allows operators to be able to swap out services as they see fit, enabling us to really gain resiliency and agility. So the possibility to attach and detach bound resources at will, depending on what we need. So how can we do this? Well, we need to be treating backing services as attached resources, and we can use things like microprofile config to help with this. As I mentioned, you can store things like the URLs, etc. in an application's config. So by externalizing that from our application code using things like microprofile config, we can enable that nothing within our code needs to change if that backing service needs to change. So again, if you want to check out microprofile, go for it. Environmental parity is number 9. So this one links into dev prod parity in the original 12 factors. And this has been sort of extended to ensure that we're not just thinking about development and production, but we're also thinking about the various other environments and deployments we have. So staging, QA, DevSecOps, all of them. And this factor is all about keeping those environments as similar as possible. And the purpose of really applying rigor and discipline to your environment parity is to essentially give you and your entire team the confidence that your application will work everywhere, no matter which environment it's deployed into. Often, when some organizations deploy into various different environments, they might use different tools, for example, but really these differences between the various environments mean that you might experience unexpected errors because you're not testing your application as it would be in production. So it's really important to keep all these environments as similar as possible to reduce that parity. So why is this important? Well, as I said, it really helps to lower unexpected errors that might occur and helps to support that continuous deployment pipeline. And it enables greater resiliency for our applications and reliability. So how do we go about enabling this factor? Well, we need to ensure that the same backing services are used for all of our deployments. So us as developers, we need to ensure that. We need to ensure a solid continuous integration pipeline between all these environments and deploy to production as often as possible. We can make use of things like automated CI/CD pipelines to help with this, and things like container tools also help. So tools like Docker can help to make production-like environments way more accessible to developer workstations. So there are tools like test containers and microshed testing that enable us to utilize a production-like environment utilizing containers and Docker on our local machine so that we can test in an environment as close to production as possible, minimizing this parity. So if you want to check out microshed testing, for example, which is utilizing those test containers to be able to test in, then check out the guide here through the link. Administrative processes. What is this all about? Well, this is linking to the original 12-factor app factor, which is admin processes. It's just been lengthened here. So this is all about running admin or management tasks as one-off processes. So storing configuration for those admin tasks within the app's code base. So for example, doing like one-off debug tasks. Why is this important? Well, it enables us to safely debug or admin of production applications and enables us greater reliability. How can we achieve this factor? Well, Kubernetes tasks can be used for this, for example, or you might be making use of an alternative like Lambdas, for example, AWS Lambdas. What about number 11? Number 11 is called port binding and is exactly the same name as the original factor, which was port binding. So what is this all about? The principle of port binding really asserts that a service or application is identifiable to the network by a port number and not a domain name. So your cloud provider should be managing the port assignment for you because it's likely also managing routing, scaling, high availability, and fault tolerance, all of which require the cloud provider to manage certain aspects of the network, including things like routing host names to ports and mapping external port numbers to containerized internal ports. So an application developed with exported port binding in mind really supports this environment-specific port binding without needing to, again, change any code, which is really important if we're going to be changing where this application is being deployed to, where it's being hosted, etc., which is often the case in cloud environments. So why is this an important factor in cloud-native applications? Well, it enables ops efficiency. The reasoning is that domain names and associated IP addresses can be assigned on the fly by manual manipulation and automated service discovery mechanisms. How do we go about enabling this factor? Well, we need to be exporting services via port binding. So microprofile config can help with this. You can specify the new port in Kubernetes config map, and then microprofile config automatically picks up the value to give the correct information to the deployed microservice. You can also make use of microprofile REST client, which can help with creating client code to connect from one microservice to another. Okay, so what about factor 12, stateless processes? Again, this links into the original factor, processes, so we just added the word stateless here. Microservices, it can be argued, should be stateless. REST is a really well-adopted transport protocol, and JAX-RS can be used to be able to achieve a RESTful architecture. So systems that are able to follow the REST paradigm can be stateless. And in this way, any underlying infrastructure can destroy or create new microservices without the risk of potentially losing state or any information. So this factor is all about executing the app as one or more stateless processes, and ensuring that all stateful data is stored in some kind of backing service. So all long-lasting state must be external to the application, provided by backing services. So the concept isn't that state can't exist, it's just that it shouldn't be maintained within your application. Why is this factor important? Well, it helps to reduce deployment complexity, reduce operational complexity, and allow for much simpler scaling, enabling sort of cloud compatibility across various different cloud platforms, enabling greater flexibility for you. How do we go about enabling this factor? Well, we need to be storing any stateful data we do need in backing services. Don't use things like sticky sessions or the local file cache. Don't use things like in-memory caches. Storing in-memory cache that your application thinks is always available can end up bloating your application, making each of your instances take up way more RAM than is really necessary. You can use things like third-party caching products like, for example, Gemfire or Geode, which is the open source version, Jcache and Redis, and all of them are designed to act as a backing service cache for your applications. So there are lots of open source tools available if you do need state of any kind. So there's lots of different, you can also take a look at the microprofile REST client to be able to enable you to build sort of stateless applications. Number 13 is concurrency, and again, it links into the original factor, concurrency. So what is this one all about? Well, this is about really being able to scale out via the process model and treat processes as first-class citizens. So what do I mean by that? Really, it's advising us that cloud-native applications need to be able to scale out using the process model. So there was a time when if an application reached the limit of its capacity, the solution was just to increase its size. If an application could only handle some number of requests per minute, then the preferred solution was just to make the application bigger, adding CPUs, RAM, and other resources to a single monolithic application, and this was referred to as virtual scaling. And this type of behavior is really typically frowned upon by society these days. A much more modern approach, one that's really ideal for the kind of elastic scalability that the cloud supports, is really to scale out horizontally rather than vertically. So rather than making a single process even larger, you can create multiple processes and then distribute the load of your application among those different processes. So microservices should be able to be scaled up or down depending on the workload. So this really allows for easy horizontal scaling and auto scaling, which can be really helpful in cloud environments when your load is rapidly changing. How can we enable this? Well, we need to split out our application into separate runnable processes and scale them independently. So we can use things like Kubernetes Autoscaler to be able to help with this. Factor 14, telemetry. This is one of the new ones. This is the second new one I've introduced here. So telemetry, logging is already a factor that we mentioned. It's been kept in the 15-factor app methodology, and it is a good start. But it's generally a tool that you use during development so that you can diagnose errors and code flows. Logging is really typically orientated around the internal structure of your application rather than reflecting sort of real-world customer usage. So in short, logging is how you collect data about your app in the lab, instrumenting your app for telemetry, on the other hand. So on the other hand, telemetry is more about how you collect data once your app is released into the wild. So the concept of telemetry wasn't among the original 12 factors. It's been introduced now that we have sort of greater evolution within our infrastructure. So building applications on your workstation affords you luxuries that you might not have in the cloud. That's why it's really important that we have telemetry in this distributed environment. It allows us to inspect, it allows us to basically have access to how our application's doing, whether that's health or metrics. So when it comes to your application, there are various different categories of data that we can collect. Application performance monitoring, for example, that might be the number of HTTP processes per second, or domain-specific telemetry, like how many products were sold via the iPad in the last 20 minutes. We can also get health and system logs, so system health check information, event information like start, stop, scale, etc. Why is this factor important? Well, as I mentioned, modern applications are getting more complex, and these applications and supporting environments are composed often of hundreds, if not thousands of microservices. It's extremely highly dynamic and distributed, and we need to be able to scale automatically to meet our users' needs. So applications are more important than ever, and all companies have applications that are mission critical. So if these applications aren't monitored and the performance degrades or it crashes, revenue is potentially at stake here, and possibly bad press and call-outs on social media, which we want to avoid. So customers are now expecting more features more rapidly and for them to work all the time. So only monitoring can really give us the real-time feedback we need to be able to quickly understand how customers are reacting to that new feature and if its performance is optimal, and enable our cloud applications to be constantly audited and monitored to ensure that they're working as expected. How can we enable this? Well, we can utilize things like microprofile metrics and health, two different APIs there within the microprofile specification, and they can enable us to collect this distributed data about our application. So we can utilize both logs and telemetry to enable us to gain information about how our application's doing. So both very important in this modern infrastructure. And the last factor, authentication and authorization. There's no discussion of security, authorization, authentication in the original 12 factors, but security is a vital part of any application and cloud environment. Security should never be an afterthought. And so a cloud-native application has to be secure. So your code, whether it's compiled or raw, is transported across many different data centers. It can be executed in multiple containers and accessed by often countless clients. some legitimate, but some nefarious. So in an ideal world, all cloud-native applications would secure all of their endpoints with RBAC, role-based access control. Every request for an application's resources would know who is making the request and the role to which that consumer belongs. So these roles can be really helpful in dictating whether the calling client has sufficient permission for the application to honor the request, and RBAC is a really useful tool for this factor. This factor is really focused on adding that additional security to applications through authentication and authorization of users, enabling us to increase security of our application. How do we do this? Well, as I mentioned, securing endpoints through RBAC can be a really great way of securing our application. We can also make use of various other tools like OAuth 2, OpenID Connect, Keycloak, IBM App ID, Azure Active Directory. There are loads of different types of tools that you can make use of. You can also make use of microprofile JWT, which is JSON Web Tokens, to be able to authenticate and authorize and verify users. So that's another open source tool that you might want to utilize. So, how do we actually enable each of these factors and the behaviors that I mentioned that enable us to create cloud-native applications? So here is a basic mapping of an application, whether it's on a public or a private or a hybrid cloud. This is just to show you the sort of pipeline of delivery of an application and running that and deploying it in the cloud. So you can see the arrow here, which is pointing into the bulk, sort of loosely represents our delivery pipeline. And we've got things like repositories where we're going to pull artifacts from or push artifacts to, etc. Now, if we map on those 15 factors that we mentioned, you start to see where they come into play in this pipeline, in this mapping of our application. And you can see where they start to enable the various components and behaviors we need. So if we map on top the behaviors that each of those enables, we can start to see how utilizing these 15 factors can enable us to enable in our application the behaviors that we want in cloud native apps. That word diagram that I showed right at the beginning of this presentation, you can see how enabling these factors enables those behaviors, which enables us to build cloud native applications that thrive in the cloud and not just survive in the cloud. And we can utilize lots of the different technologies that I mentioned throughout this presentation to enable that. And you can check each of those out if you'd like to. If you want to get hands-on experience with each of them, we do have some interactive cloud native labs that you can check out through this link here or through the OpenLiberty website. They're all based on the OpenLiberty guides. OpenLiberty is our open source web application server. So this is all open source, and many of the guides here make use of other open source technology that I've mentioned in this presentation. So check those out at openliberty.io/guides. Hopefully, in summary, what I've shown you throughout this presentation is that the 12-factor application methodology is a fantastic place to start. But to really thrive in the cloud, we need to be looking beyond the 12 factors at those additional factors and those additional edits made to the factors to really make use of that modern underlying cloud infrastructure. And there are no excuses. I've mentioned a bunch of open source tools here. So really, you should be able to make use of at least one of them within your application to help you to enable those behaviors that we need for applications to thrive in the cloud. So hopefully I'd like you to take away that the action today is really to evaluate your own application against each of these 15 factors and consider what you could do to really enable your application to truly thrive in the cloud. If I haven't given you enough homework already, then if you want any additional information, I've added some useful resources here and I've split them out into some of those factors. So you can just identify the factor you're interested in and check out the links that are relevant to you. Thanks very much for listening. It's been a pleasure joining you today.